By Newton's first law of motion, we know that a force is necessary to change the direction of an object. If you throw a ball upwards, it will always return towards the earth. Have you ever wondered what causes the ball to change its direction? Let's find out. Newton very humbly said that his work is based on the observations and research carried out by two great scientists, Galileo and Kepler. He came to an important conclusion that any two particles with masses m1 and m2 attract each other by a force whose magnitude is directly proportional to the product of the two masses, that is, m1 into m2, and inversely proportional to the square of the distance between them, that is, r squared. The direction of force is along the line joining the two masses. This law is known as the universal law of gravitation. C1, C2 is a line joining the centers of mass m1 and m2. Thus, C1, C2 is equal to r, and the gravitational force will be acting in the direction along C1, C2. Let F1 be the force on m2 due to m1 in the C1, C2 direction, and let F2 be the force on m1 due to m2 in the C1, C2 direction. Both these forces being equal in magnitude, F1 is equal to F2 is equal to F. The law of gravitation states F is proportional to m1 into m2, and F is proportional to 1 upon r squared. Therefore, F is proportional to m1 m2 upon r squared, or F is equal to g into m1 m2 upon r squared. Here, g is a constant, and g does not depend on the values of m1 m2 or r. Therefore, g is equal to F upon m1 m2 upon r squared. If we measure distance in meters and mass in kilograms, we get the unit of force in Newton. Thus, the unit of g is Newton per kg square per meter square. That is, Newton meter square per kg square. Constant g will remain the same for any two objects anywhere in the universe. So g is known as the universal constant. Its value is very small. The scientists have determined its value from the experiments carried out very carefully. Two massive spheres of gold were suspended, keeping them very near. The force between the two spheres was measured. The experiment with gold balls gave the value of g is equal to 6.67 into 10 raised to minus 11 Newton meter square per kg square. Knowing this value of g, we can now calculate the force of attraction between the two bodies. The force between you and your friend, let m1, that is your own mass, be 35 kgs, and m2, that is your friend's mass, be 40 kgs. R is equal to 1 meter is equal to the distance between you two. Using F is equal to g into m1 m2 upon r square, we have F is equal to 6.67 into 10 raised to minus 11 into 35 into 40 upon 1 square. Which is equal to 9.338 into 10 raised to minus 8 newtons. The force between you and the earth, let m1 is equal to 35 kg, that is your mass, and m2 is equal to 6 into 10 raised to 24 kg, that is the mass of Earth. R is equal to radius of the Earth, which is equal to 6.37 into 10 raised to 6 meters. Using the equation F is equal to G into m1 m2 upon r square. Thus F is equal to 6.67 into 10 raised to minus 11 into 35 into 6 into 10 raised to 24 divided by 6.37 into 10 raised to 6 whole square is equal to 345.2 Newton. This force is about 10 raised to 10 times the force between you and your friend. The force with which you and the Earth attract each other is almost 1,000 million times stronger than the force of attraction between you and your friend sitting next to you in the class. We can ignore the force between you and your friend, but we certainly cannot ignore the force between you and the Earth. Let's summarize. In this session, we have learned the universal law of gravitation, which states that any two particles with masses m and m2 attract each other by a force whose magnitude is directly proportional to the product of two masses and inversely proportional to the square of the distance between them, and can be represented as F is equal to G m1 m2 by r square. We also learned that the direction of force is along the line joining the two masses. The phenomenon of attraction between different bodies in the universe is called gravitation. We will study the special cases of gravitation when one of the two bodies happens to be the Earth. Stay tuned to learn more.